Unas preguntas. Okay, let's start. Welcome everyone. We're happy today to have with us Antonio Acín. I'll give you a brief introduction about his curriculum. So Tony studied in the University of Barcelona physics and in the Universitat Politécnica Catalunya telecommunications engineering. Then he did his PhD with José Ignacio Latorre as a first student on quantum information theory. And after 2 years of postdoc in Geneva, he came back to Spain to lead the quantum information group at ICFO, where he still is now as ICREA professor. His work focuses on quantum communication and quantum cryptography. He is particularly known for his device-independent approach that he will talk about, that is able to certify security of cryptography schemes without knowing really the microscopic details of your devices. So this is really the most secure way to obtain quantum key distribution, for example. But also he has made important contributions to other areas related to quantum information, quantum many-body physics, quantum thermodynamics, the foundations of quantum physics, and also quantum optics. And his research has been very successful. He has obtained various awards and grants. I only mention a few of them. So he is an ICREA professor. He has obtained 4 ERC grants, a starting grant, a consolidator grant, an advanced grant, and a proof of concept grant. He is AXA Chair of Quantum Information Science, and now recently, just last year, he was awarded the Jaume Primer Award, which he will receive tomorrow, and that's the reason for his visit. So, Tony, we're very happy that you're here. Looking forward to your colloquium.
Okay, thank you very much, Manuel, for the introduction, and thanks for hosting me here. I believe it's my first time in this institute. And as Manuel said, I will tell you about what has been one of the main things in my group, which is this device-independent approach. And so the scope of my thesis, of my talk, is to tell you about this approach, why we care about this, and what we learned working in this approach. So I will start by just, I believe that many of you are not working on quantum information theory, so I will start by some general slides about the field. So basically what the field wants to understand is what happens when we make this transition from the hour scale to the macroscopic scale of atoms and photons. And physicists, we have already done this transition in the past. This was quantum physics. So we have to go from here, there. So we have to change Newtonian physics, and the founders of the theory found the quantum theory, okay? And so we know that this is well established in physics. So now we want to do the same for information processing, okay? The reason why we care about this is because now we can put information on quantum particles. I always spend some time when I present this, because this is okay. It's a bit annoying, no? Is it okay? Okay, good. So I want to spend some time here because I think this is a change of paradigm for the way you understand information. So before I entered the field, I studied physics and telecommunication engineering, and I didn't have any course on information theory in physics. And if you had asked me at that time whether putting information on quantum particles makes a difference about the things you can do with information, at that time I would have said no. Because my understanding of information at the time was that it was something abstract, not related to physics, and that was one of the main virtues of information theory, okay? I can make a bit for you. I can encode information with these two objects. This can be 0, this can be 1. We can communicate with this. Of course, we don't do it in practice because this is not convenient, but we all understand that this is a bit as good as any other bit, because my understanding was that a bit is any physical object that can take 2 values. Okay? So I thought that basically information is more a mathematical field in which physicists, we don't have many things to say, but actually it's the opposite. Okay, so physics matters. The things you can do with information depend on whether you put this information on particles described by classical physics or particles described by quantum physics. Okay, so this might sound trivial to you. For me, it's not, and I think it's a change of paradigm the way we understand it. Okay, so now, I mean, the field has some maturity. We have made this transition, and we know that you can have some machines, quantum computers, that can solve some problems better than our existing classical computers. And we also know that we have some schemes for cryptography that I will tell you about. So we can do more things when we put information on quantum particles when we use what are called quantum bits or qubits. This is well established. So physics matters when you care about information processing. So the field is advancing. Now there were first theoretical ideas, then people made experiments, and then these experiments now are becoming commercial products. So you can now buy quantum computers. There is something called quantum simulator. I'm not going to spend time about it, but it's like some sort of special purpose quantum computer. You can secure your messages using quantum cryptography. You can also generate random numbers based on quantum physics, quantum random number generators, and you can buy these devices. Actually, these two devices come from Lux Quanta and QSci, that are spin-off companies from my institute, ICFO. Okay, so advertise a bit what they are doing. At the moment, these are companies that are growing, and they are selling these products for you. I mean, they are not cheap, okay? You are going to spend some money if you want to buy them. Okay, so once the field is advancing and we have these products, then there is a problem that emerges, which is the problem of quantum certification. So you are going to pay a lot of money for these devices, and they are supposed to achieve a task that you cannot achieve with current devices. How do you know that they achieve what they are supposed to do? Okay, so if they sell you this box, I mean, you won't see this, or they sell you this, how do you know that this is a quantum computer, that it is cryptographically secure, or that this produces quantum randomness? Okay, because think about what happens here. Okay, you are the user, you go to the provider, and you say, like, okay, give me a quantum random number generator. The provider will tell you, sure, here you have a quantum random number generator. You will get a box, right? You will look at the box and say, is this quantum? And the provider will tell you, yes, it is. Okay? So, and again, you're investing money for tasks that are supposed to achieve something quite complex. Okay, so this is a very important problem at the moment. It's quite transversal to the field. Okay, we want to understand that things behave as expected, also because the technology is not mature. Okay, so also even for not only as a user, but even when for experimentalists trying to implement these technologies, they want to certify that things go as expected. We know that controlling quantum phenomena is under some control, but it's still challenging. And I'm going to spend some time to motivate my problem here for random number generators, and then I will go to cryptography. And we are also working a bit on certification of quantum computers, but I will mostly focus on cryptography. And I always use this joke that I also used yesterday for the general public talk, because I think it's excellent to describe what I want to tell you, okay? So this is you as a user, you go to the provider, okay, and this is the device that is selling you. Okay, it looks like a weird device, okay, but you should understand this is the box you will get, okay, from the provider. And you want to buy a random number generator, and then you say, okay, here you have it, 999, and you wonder whether this is a proper random number generator. It doesn't look like, but you know that the probability that a good random number generator gives you this sequence is the same as any other sequence. Okay? And the provider tells you, well, it's tricky to certify that something is random, which is true, okay, in classical physics. But as you will see, this is possible in quantum physics. Okay? So basically what we want to do here, in this particular context, is we want to certify that this produces randomness of quantum origin. More in general, we want to certify that the device behaves as expected from the outputs we see from the device. Now, if you think about you buying a device from a provider, the way even if it's quantum technologies, the way we interact with devices is through classical information. Okay? So even if you have a quantum experiment in your lab or an accelerator, you press buttons or you write instructions on a keyboard. Okay? You never give a quantum state. You perform some actions, and these actions are labeled by classical information. And then something happens quantumly, but at the very end, you read this information, you make a measurement, and you have a click on a given detector. This is again classical information. We never see superpositions. We never give superpositions to an object. We always deal with quantum information. So this is important to understand. Okay, so when I say the outputs, I mean these are classical outputs because quantum data, we don't see quantum information. We measure and see classical information. To understand another motivation for this problem, I'm giving you one based on random number generators. Now I'll give you another one based on cryptography. I'm going to give you a very short explanation about what quantum cryptography is. It's not so relevant for my talk. I mean, not everything is I mean, you can simply get a flavor of what the quantum cryptography protocol does. So basically, this is a situation in which there are now two users, Alice and Bob, and they want to exchange what is called a secret key. So they want to have each a list of bits that is identical and perfectly correlated. So let's imagine that Manuel is in Valencia, I'm in Barcelona. So whenever I have a 0, he will have a 0. Whenever I have a 1, he will have a 1. Okay. And the way we achieve this in the protocol invented by Bennett and Brassard in 1994 is called BBT4. So, okay, now the usual user will call Alice and Bob. Alice sends zeros and ones into quantum particles. To understand what is going on here, you can understand this quantum particle as a spin 1/2 particle. It can be pointing z, minus z, x, minus x everywhere, but Alice only uses 4 directions. I understand everyone follows what I'm saying. This is very basic quantum physics. And then you put this information on these quantum particles. They might be pointing plus z, minus x, or plus x, and Bob measures the spin of this particle in the z and the direction. Okay? And it happens that when Alice and Bob use the same basis to encode the information and to read the information, if you have a particle pointing in z and you measure in the z direction, you will get plus z with probability 1. Okay? But if you measure in the x direction, if you have a particle z and you measure in the x direction, you know that you get half the probability. Okay? So you only keep those instances in which the bases match, and at the very end you get a 0 and a 1. Okay? Zeros and ones that are perfectly correlated. Okay. I'm going quite fast. The only thing I want you to remember from this slide is that in this protocol, Alice and Bob prepare qubit space living in a 2-dimensional space. This is prepared by Alice, this is sent to Bob. Bob makes a measurement, and out of this process, they get the secret key. You see, whenever Alice has a 0, Bob has a 0, whenever Alice has a 1, Bob has a 1. And then you can mathematically prove that an enemy who wants to have the same bits, she cannot do it. Okay, so these bits are known by Alice and Bob and only known by Alice and Bob, which means that the key is secret because they are the only ones knowing this list of bits. Okay, the only thing you have to remember is that by exchanging qubits, you can mathematically prove that Alice and Bob have this list of perfectly correlated bits, and they are the only ones who have access to this list of perfectly correlated bits. The enemy does not have a copy. Okay, because the enemy, what she has to do, somehow, this is the first explanation of quantum cryptography, the spin 1/2 particles go from Alice to Bob. The enemy has to read a spin that might be pointing in the z or x direction. And if you remember, you cannot measure z and x direction of a spin at the same time. It's more or less why the protocol is secure. I mean, it's much more complex than what I'm saying, but this is for you to understand intuitively why the protocol is secure. It just follows from the Heisenberg uncertainty principle. Okay? So because it's impossible to measure in the z and x direction at the same time. Also, when I give a talk to a more general public, this is something that I like it for the field. It's like, personally, when I saw the Heisenberg uncertainty relation, I never liked it. I don't know if you liked it when you saw it the first time. I always find that it was something weird about quantum physics. Here, you use it to make something useful to make cryptography. Okay, so quantum cryptography is also a change of paradigm. You base the protocol on Heisenberg uncertainty relation, so you base the protocol on the laws of quantum physics. The protocol is secure because whatever the enemy does, she will be constrained by the laws of quantum physics. So this is your assumption. You believe that the laws of quantum physics are correct, and then you don't have to say anything about the enemy. You only have to assume that the enemy cannot break the laws of quantum physics. And then using these formalities, you can prove that the key is secure and it can be used for cryptography mathematically. I'm not giving this proof, but you can prove. Okay, yes. You can prove that the protocol is secure. So what you want to remember is that you assume the validity of quantum physics. This is for us, it's not an assumption, but okay, it's an assumption, okay? And from that, you mathematically prove security. And you can now buy cryptography and you can exchange messages using quantum key distribution. Good? Some years ago, there were several teams in the world, in particular, Vadim Makarov, who is here, was very active on that. He went to one of these companies selling quantum cryptography, and they showed that he could hack cryptography. Okay? So that was a surprise for the community. I mean, for instance, I wrote papers talking about unbreakable security. Okay, now I feel ashamed of writing these papers. I could go backwards in time, I would erase all what I wrote there, okay? But I wrote this, and he was proving that things were not as nice as we expected, okay? So they made an article in Nature Photonics. Also, Nature was writing about this because it was sort of shock for the community. So usually when you have cryptography, a cryptographic solution is not mature if it has not been exposed to hacking attacks. Okay, so hacking attacks are good for cryptography, especially if the hackers collaborate with you, and they did collaborate with the good guys, that is us. Okay, so what did they prove? Okay, so now you have to understand how come they could hack quantum cryptography. Because look what I was telling you. It's based on the validity of quantum physics, and you can mathematically prove security. But he hacked it. So there are several possibilities, okay? The first one is that he found a mistake in the mathematical security proof. Now, does he look like a mathematician? Not really. You see many devices around him. He's not a mathematician, he's an experimentalist. Okay? Very far from mathematics, an experimentalist. Okay, so there are this other possibility. He's an experimentalist. He proved he falsified quantum physics. For sure, this is not what happened. He would have won the Nobel Prize. Okay, I mean, you didn't know about Makarov. Okay, you would know about Makarov. He had broken quantum physics. Okay, so this means that here I was too naive in my explanation of quantum cryptography, and this is what we learned from the hacking attack. So what the hackers did, they broke the implementation but not the principle of quantum cryptography. And now I'm going to tell you what I mean by this, okay? So you remember my brief explanation about quantum distribution. I was telling you that Alice prepares states of spin 1/2 particles, okay? These are called qubits in a two-dimensional space. And I prepare these states, I send them to Manuel, and Manuel measures sigma z and sigma x. These are standard Stein-Gerlach von Neumann measurements that we all know from textbooks in quantum physics. Okay, this is the description of the protocol. Now you go to what you do in practice. To prepare the qubits, usually people use lasers. Okay? For instance, the polarization of a light pulse that has been produced by a laser. Okay, a photon does not live in a Hilbert space of dimension 2. Nothing lives in a Hilbert space of dimension 2. Nothing has dimension 2. Okay? A photon has polarization, but it has frequency, it has orbital angular momentum. We all have many degrees of freedom. Proving that something has dimension 2 is impossible if you think about it. So it's impossible to. Dimension is a mathematical artifact that we use to model experiments, but we cannot measure dimension. So people prepare states with a laser source that doesn't live in a Hilbert space dimension 2, and then they measure the light, and the light is prepared at a single photon level. You have single photon detectors. A single photon detector is not described by a 2 × 2 matrix that you use to describe sigma x or sigma z. Okay, it's a much more complex object. So a gap appears between the theoretical description of your protocol and the implementation. So where do you have the theoretical security proof? Here. But what do the hackers need to break the implementation? So for them, you could argue that it's almost irrelevant the existence of theoretical security proof if the conditions of the implementation don't meet the theoretical condition under which the theoretical security proof has been derived. So what we learned is that it's very nice to base your security on physics. I'm a physicist. I like a protocol in which the security is based on the laws of quantum physics. I like it. I believe the laws of quantum physics are valid for the scales used in the protocol. But if the security depends on all the physical details of my devices, this may be a problem. Because unless my implementation meets all these conditions, then I cannot claim that the implementation is secure. Okay, so the problem was the existence of this gap. Now, how can you close the gap? And this is what we propose. This is the device-independent solution. But don't make assumptions about your devices. Don't model them. Don't say that they have Hilbert space dimension 2, 3, 4, 100, infinite. Just see your devices as black boxes. This is exactly what happens, no? When you go to the provider, you get a box. You are never going to open the box and see, I see the qubits flying from one place to another. I see. You're never going to do that, okay? You're going to get the box. If you can make quantum information protocols or cryptography protocols in this language, then this gap disappears. Okay? Because you don't say what is happening inside the box. What you say is independent of the devices. So this is what we proposed some years ago, and this is why it's so relevant for cryptography, because all these hacking attacks exploiting mismatch between theory and implementation disappear in this language. So we want to do something I call it a quantum information theory with black boxes, or a quantum information theory. I'm not going to specify any Hilbert space without Hilbert spaces. Still, I have to say something about these devices. Well, I will say that the users interact with these devices, and as I was telling you, the way we interact with devices is through classical information. So for you to understand, this is what I usually explain, is like you can think of these devices as a black box. This black box has some buttons, M buttons, and the way to interact with the box is you press one of the buttons. And then at the bottom of the box, I mean, this is a way of seeing what I wanted to tell you, okay? You have lights at the bottom of the box, and when you press one of the buttons, one of the lights is on. Or this box has a knob that you can put in different positions, and when you put the knob in a given position, the box gives you a musical tone or a color. Okay? So you interact with an input and you get an output. So you don't attribute any meaning to this input-output. You just say that you have n possibilities and you get r possible results. What happens here, how the output is produced given the input, I don't know, and I will never know, because I'm never going to open the device. It will be a quantum process, because I'm a quantum physicist. So there is a quantum process here with a given Hilbert space that I don't know, that produces the output given the input. So the way we characterize our experiment is only with the statistics we see. Similar to, you remember the demon saying 99999? This is what we see. I see when I press a button and when I see a light. This is the only thing I can trust. So what Manuel and I, what we will do, we will keep some time pressing buttons and seeing the lights. And out of this, we will construct the probabilities of me seeing result 1 and him seeing result 1 when we press button 3 and he pressed button 5. These probabilities. If I can make a protocol secure based on these probabilities, this gap disappears. Because all what the theoretical description requires are the observation of these probabilities, and all what the implementation achieves is these probabilities. Okay? So there is no gap. Because I don't make any assumption about what is going on here, because the protocols are device independent. Okay, so this is why we propose these formalities, just to avoid any problem with hacking attacks, and if you think more about it, more in general, because we want to certify devices only from the statistics that they produce, that the daemon producing randomness. Okay, so this was the motivation, a long introduction for the motivation. Now I will tell you how we do these things. Okay, because it sounds like very minimalistic, okay? You only have these black boxes and you give classical information, get classical information. Okay, why is this possible? Okay, so now I'm going to do something very basic, and all my talk, maybe if you care about the fundamental laws of physics and something like this, it sounds very boring. I'm telling you about users, providers, technologies, okay? And you are more on the fundamental level. Okay, now I'm going to be a bit more fundamental, okay? So in my story, I'm telling you there are the two users that go to the provider and they buy these devices and they interact with these devices with the inputs and outputs and they get the statistics. Okay, now I'm going to do something very simple. I'm going to call the provider a source. So the source produces two particles and you make measurements on these particles and you get results. What is that? This is Bell theorem. Yes, you all know about the Bell quantification. If not, I will tell you quickly about it. So the same language that I use to explain a practical situation with users and providers is what happens in a Bell experiment. There is a source that prepares two particles. These two particles go to different locations, and you make measurements and you get outputs. It's the same language. And you collect the statistics, and these statistics, in the classical case, satisfy some Bell inequalities, in the quantum case, it will violate this inequality. It's the same language. So this is something that the Bell test. And what we learn from the Bell test is that what the statistics you generate in this experiment depends on the physical theory that describes the devices. Okay, and now we will spend some time on that. Okay, because what we learn is that the probabilities you see between these two devices, that I'm going to call the correlations you see, how the devices behave at distance, depends on the physical laws describing the devices. I think this is also one of the main lessons of Bell's theorem. Physical principles impose limits on statistics, on correlations. I'm going to call these correlations during my talk. It's just this vector of probability. So, what is the object we deal with in this device-dependent approach to quantum information theory? Again, it's these statistics, okay? There is a Hilbert space behind the generation of these statistics, but I'm never going to describe it. I don't want to assume it. So the description is very simple, okay? So here, these people will spend some time pressing buttons and seeing lights, okay? Or putting inputs and getting outputs. So for instance, they use input 1 and 1, and they see what is the probability of getting result 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on, so on. Okay, so now I'm taking, these are probabilities, so these are positive numbers, and you sum, they have to be normalized, so this sum has to be equal to 1. Okay, so these are the probabilities, if you want, of observing some results when you make measurement 1 and 1. This is very trivial mathematics, what I'm doing at the moment, okay? You will have another vector of probabilities when you use input 1 here and 2 here. Again, you will have 1, 1, 1, 2. Some probabilities may be 0 here, okay? But these are positive numbers summing to 1. For all combination of inputs, you have all combination of outputs with some probabilities. This is a long vector of numbers or a matrix, doesn't matter. Numbers are positive, and if you sum this element is equal to 1, if you sum this element is equal to 1, if you sum this element is equal to 1. Trivial mathematics. Okay, this is the main object in my talk. I'm going to talk about these correlations. Okay, so let me give an example. The simplest example in which you put a bit and you get a bit. I'm going to call this output bit plus and minus 1. The input I'm going to call 0 and 1. I can call it 1, 2, 3, and 5. It doesn't matter, okay? It's just a label. So you have this experiment in which you choose to make two possible measurements of two outputs. When you put an input, you get an output bit. Let's assume that when both use 0, if Alice gets a plus, Bob gets a plus, and this happens with probability half. They simply put 0, and they see that sometimes Alice gets a plus, but whenever Alice gets a plus, Bob gets a plus. Half. But they also see that when Alice gets a minus, Bob gets a minus. Half. So what is the value of these probabilities? Well, I do more complex calculations than this, okay? This is very simple. But we all understand that they have to be 0 and 0 because these probabilities cannot be larger than 1, okay? Let's assume I'm inventing these numbers for you, okay? It's not a super funny thing what I'm doing, but I can invent for you. Let's assume that the same happens when they use 0 and 1. The same happens when they use 1 and 0. And now, for fun, when they measure 1 and 1, whenever Alice sees a plus, Bob sees a minus. Whenever Alice sees a minus, Bob sees a plus. Okay? I can't spend time here inventing these tables of probabilities. It's not funny, but we can do it. Does anyone see anything weird with this matrix? It could happen, no? We have an experiment, we make two measurements, we get two outputs, very simple experiment, and we see this table of probabilities. Okay, this is an example of correlations. Good. Now, we are physicists, I believe, all here. Let's use what we know about physics. And this, okay, so this object cannot be arbitrary if these devices are physical devices. So in all my talk, I'm going to assume that what I do here is not causally connected to what Manuel does, because I'm in Barcelona and he's in Valencia. So what I do in Barcelona does not affect what he sees. If you want to think physically, I'm assuming that the events are space-like separated. There is no time, not even for light, to travel from one place to another. But okay, I'm going to assume simply that things are causally disconnected, because I assume that what I do in Barcelona does not affect what he sees in Valencia. So this means that my action does not change what he sees, okay? I cannot signal to him by doing actions in my device. If I can see what he sees by doing actions here, I can transmit information to him. I'm assuming that this is not happening. Okay, this means that what he sees, the marginal probability distribution, does not depend on what I decide to do in my box. You see, the marginal distribution does not depend on the input of the other party. Okay, this is called no signaling condition. It's just telling, in general, that if you sum over my results to describe what it is, this does not depend on what I do. This is a very simple mathematical condition, but it's a mathematical condition. Okay, so these numbers have to satisfy this mathematical condition. Let's go back to the previous metrics that I wrote innocently, okay? But you will see that it's not so innocent what I wrote here, okay? Let's see if these parties having access to these boxes behaving in this way, they can use them to signal. Let's compute the probability that this device sees +1 when you use input 0 here, okay? So this, I guess everyone can follow here, is the probability of having ++ and +- and summing over the results of the other device, okay? When you use input 0 here and input 0 here. So this is the sum of these probabilities, the sum of these probabilities is equal to 1/2. This has to be the same if this party uses 1. Okay, because this party cannot affect what this party sees by choosing different input here. So this is imposing that the sum of these two numbers has to be the sum of these two numbers. Oh, surprise, they are equal, okay? Well, this is because my chosen half and 0 was not innocent and was choosing to satisfy all the conditions that you need. So this probability distribution, these correlations do not allow signaling. They are no signaling. Again, if you put random numbers here, you won't satisfy the constraints. Okay, you have to do it carefully so that you satisfy these constraints. So these correlations are not arbitrary if you live in a world in which people cannot communicate at distance. How were correlations conceived before quantum physics? Well, before quantum physics, what we thought is that we go to the provider gives the devices, and these devices have a program, or you can think of a small demon sitting inside the device with a piece of paper, and then the demon sees the input, looks at the paper, and the paper says, if input is equal to 3, output is equal to 4, and the demon gives you this output. Or a program written where you if do that. Okay, so this means that what the box produces is a deterministic function of the input in the program, and maybe this program has some probability, some stochastic factor I can put here to not lose generality. So this is the way we conceive correlations before quantum physics. This is what are called local hidden variable models, the Einstein-Podolsky Rosen correlations. I mean, people use locality, realism, I don't know if you read the papers. Well, to me, it's simply common sense applied to correlations. I used to think that correlations are because in the device, something tells how to produce the output given the input. I don't know. You know, this is a set of what I'm going to call classical correlations. These correlations are bounded by the inequalities. I don't know if I was told that there are papers by Boole, the inventor of Boole algebra, in which he derived Bell inequalities before quantum physics, okay? Because Bell inequalities, if you know about Bell inequalities, have nothing to do with quantum physics, are limits on classical correlation. What is quantum is the violation, but the Bell inequality has nothing to do with quantum physics. Okay? So this is, to me, common sense applied to correlations. But we are quantum physicists. We know that if we make an experiment on two systems, these two systems are described by a Hilbert space, and my measurements are described in Hilbert spaces. And we know that if we make measurements on two different devices, the correlations can be written as tensor product measurements acting on a state. I'm not saying this is a qubit, q-treat, q-quark. Some correlations are quantum whenever there exists a state in a given Hilbert space, maybe of infinite dimension. Measurements for me, measurements for Manuel. I combine this with the Born rule, and I get these numbers. This is a set of quantum correlations. Okay, you see, these probabilities get some structure based on the physical theory you did assume for the correlation, for the generation of the correlations. So what do we know about these sets? We know that they're convex, all of them. So I'm very bad drawing, but the black set is the set of classical correlations, the red set is the set of quantum correlations, and the blue set is the set of non-signaling correlations. We know that classical correlations are included in quantum correlations, this we know, but they are strictly included. And we know that quantum correlations are strictly included in non-signaling correlations. So I can zoom in this part here, so this is the set of correlations, quantum, and non-signaling. I'm going to jump this for the sake of time. So how do we know these things? We know because of the inequalities. I'm going to give you a crash course on Bell inequalities for you to understand. I hope you all follow. I used to talk a lot, so I'm telling you, I started telling you about devices and providers, and then I jumped into sources and the structure of correlations in nature based on geophysical theory. Okay? I will then connect the two things. And for that, I will use Bell inequalities. So what is a Bell inequality? Again, you have a source, you prepare two systems, you make measurements, and you get results. So the simplest Bell inequality is called Clauser-Horn-Shimonian-Hall, CHSH, and it's described in this scenario. So basically, this is the Bell function. You take the output of this device when you use input 1, and B1 is the output of this device when you use input 1. It's the same language I'm using. I'm all the time dealing with black boxes in which you do put inputs and get outputs. Okay, so I take this weird combination of results here and here, okay, depending on the inputs. Okay, this is the combination I get. It looks very innocent. Let's compute the maximum of this function when observables have, in classical physics, okay, in classical physics, observables have well-defined values, okay, they are plus or minus 1. Okay, let's compute the maximum of this quantity. Okay, you can easily prove that this quantity is bounded by 2. So, the proof is very simple. I will do something with you. We're going to make a case, for instance. Let's assume that the demons here, the instruction they have is, no matter the input, say plus 1. It's a possible realization. So what's the number you get here? Okay, this is plus 1, this is plus 1. Plus 1 times plus 1 is equal to plus 1. Plus 1 times plus 1 is equal to plus 1, so you have 2. Plus 1 times plus 1, it makes plus 1, so you have 3. Unfortunately, minus plus 1 is equal to the minus, so you're back at 2. Again, I do more complex things than this, what I'm telling you, okay? But you understand that everything is plus 1, this number is equal to 2. You can take all possible combinations of plus and minus 1, you will see that this number is never larger than 2. Trivial mathematics, okay? I'm not doing anything weird. Or understand that this is a fact, mathematical fact. Okay, so this is the Bell inequality. Even if this changes, the expectation value of this quantity will never be larger than 2 because the maximum you can take is 2. In my general public talks, sometimes I play a Bell test with people in the room. Okay, we could do a Bell test here, and you are classical objects. I mean, maybe not internally, but you behave as classical objects. And then we play, and they never go beyond 2. Well, because it's impossible, no? When you say plus and minus 1. Okay, so I think you could even go to the street and explain these rules to people with very basic mathematical understanding, and you could bet money, and people will bet money that this quantity is never going to be larger than 2. I'm sure we cannot do that. We could do it, and I'm sure you will find people who are saying, well, plus and minus 1, they can be never larger than 2. Well, the surprising thing is that if you prepare this state and you make these measurements, this quantity is larger than 2. And this is a quantum derivation, okay? So if you are not surprised by this, my talk is a failure. I'm still surprised whenever I explain it, okay? So I have to say it's weird that quantum physics violates that this quantity goes and is larger than 2. Okay, how come these plus and minus 1s can be larger than 2? Again, it's a pity we cannot do it now, but if we could prepare this here. So when I put in the pocket and go to the street, this will be the real first application of quantum physics. You will be getting money from people, okay? Because people will be betting money that you cannot go beyond 2, and the only thing I have to do is like, depending on the input, I have to take my qubit out of my pocket, make a measurement, and depending on the result, give the output. And the people will get mad because they will see that this quantity is larger than 2. Okay. So I find it really amazing. Okay, what is this game, this CHSH game? This is this hyperplane here. And classical physics is below this value. Okay, hyperplane, below, okay, inequality. What is happening? So quantum physics violates this condition, and you know, this is why we know that the quantum set is larger than the classical set, because the classical set is bounded by this quantity. So we also know, I'm not going to tell you, that this quantity in quantum physics can go up to 2 square root of 2, precisely what I was telling you here. Okay? So this is nothing, but the hyperplane is the same, you only change the constant term in the hyperplane. Okay, you are displacing the hyperplane until it becomes tangent to the quantum set. Good. So now let me take this innocent table of probability that was invented for you, and let's compute the value of CHSH. Oh, sorry. Here, for A1, B1, the parties get either plus plus or minus minus. The product is equal to plus 1. These are plus 1. These are plus 1. These are plus 1. But for the last one, they either get plus minus or minus plus. The product is minus 1. With a minus gives a plus. So this point gives 4, which is incompatible with quantum physics. So if you make this experiment and you get these probabilities, you are falsifying quantum physics in the same way as these points falsify classical physics. So this very simple table of probabilities would be falsifying quantum physics QED, QCD, no matter what, in a single experiment. Because these probabilities are incompatible with any quantum theory. Not with qubits, qubits, quarks. They are incompatible with quantum physics. So sometimes when I give talk, people tell me, where can I find this number? Well, I wish I knew. I don't know how to falsify quantum physics, okay? But what I'm telling you is that I'm giving you the tools to prove that things are incompatible with quantum physics. Okay. And this is why we know that the set of Gaussian correlations is larger than the quantum set. Okay, so there are some points here, I can work with them theoretically, but they don't have any quantum realization with Hilbert spaces. Okay, so again, I started with providers. I now tell you things about correlation and theories of nature and what is statistic you can see in theories of nature. Let me spend some time. If I want to make protocols, I'm technology. Let's say if I want to go back to technology, I have to make protocols based on this part here. I want to do things with quantum physics. I don't know how to do these things. My theory of nature at the moment is quantum physics. And I want to achieve results that are not possible in classical information theory, so I should better work in this region. So we have to have tools to characterize this region. Well, this is something that we did already some years ago with Miguel Velasquez, who was at the time PhD in my group. Now he's a professor in Vienna, and Piedonio, who was a postdoc. Now he's professor in Brussels. And the problem is very simple, okay? So assume you are an experimentalist, or you work at CERN. You make measurements on two particles, and you get two outputs. You measure the spin of two, you believe you are measuring the spin of two particles, and you get these numbers. I mean, again, inventing these numbers like the halves and zeros, okay? Okay, so you go to the theory and say, give me a model that describes these numbers, okay? So the theorist is going to use quantum physics. He will try to reproduce these numbers with a state and measurement. Say, the theorist sees two outputs. He says, well, it has to be spin 1/2 particles because I see two outputs. He won't find any state and measurements given these numbers. So he goes back to you and says, I tried to reproduce these numbers with theory, I failed. And you say, what did you try? Well, I tried with 2 times 2 matrices. Well, maybe it was too short. Try with 3 times 3. Okay, the theory goes back to his office, tries to reproduce these numbers, fails again. He comes back to you, okay? Says, I failed with 3 times 3. Well, try 4 times 4. Okay, he goes back, 4 times 4, comes back to you, I failed. Okay, you understand that this can last forever. So what we want to understand is how we can prove that some things are not achievable in quantum physics. Okay, this is what we did, okay? And again, we did that because we wanted to characterize this region. We wanted to understand which points are not possible in quantum physics and which are possible in quantum physics. So for that, we gave a method that approximates the set of quantum correlations from the outside. Okay, so if you have a point that is not quantum, say it's here, our method at some point detects this point. So we can, again, we give you tools to falsify quantum physics. In our case, we are also interested because we want to do quantum information theory with black boxes, so we should characterize this set. And it's convenient to characterize the set from the outside, okay? Because we want to characterize what the enemy can do, so the enemy will do this and potentially something more. Okay, this is a bit too fast for you, but we have tools to characterize this set of correlations. So if you get this point, you give this point to us, we will give you a stamp. This is not quantum. So stop computing with matrices and coming back. There is no Hilbert space. Dimension 2, 3, 4, 100, infinite. that produces these numbers. Okay, so we don't know how to do it, but we have tools now to falsify quantum physics in the same way as Bell inequality is falsified. That's good. Okay, so let me now go back after this journey for foundations. Now I go back to devices and technologies. So you want to solve this problem. This problem, okay? So why is this problem difficult? So imagine you have you want to become rich, and you have a business model in which you want to have a virtual casino and a web page. Like for a virtual casino, you need random numbers because you want things that are not predictable. So imagine that I'm an experimentalist. I'm not, I'm a theorist, but imagine I was an experimentalist. You come to me and you want a random number generator. And imagine I have the technology to give you good random numbers based on quantum physics. So what I do, I generate the random numbers before you come to me. I copy these random numbers into a memory. I put this memory into a box. I paint it in fancy colors. I write quantum random number generator, and this is what I'm sending to you. So you look at it and say, Antonio Acín, is this a quantum random number generator? I say, yes, it is, okay? Okay, you don't trust me, you should never trust me. You go to your place and say, well, I want to see if Antonio Acín is trying to play with me or not, okay? So you start pressing a button, and the random numbers are produced. You want to test, you know, sometimes random numbers are tested with some statistical test. You say, I don't trust Antonio Acín, I'm going to check if the numbers are random. The numbers in the memory will pass any test because they were randomly generated. So I say, Antonio Acín, nice guy, I will use this for my virtual casino, okay? But then you use them, and I take all your money because the numbers are random to you, but they are not random to me because I generated them in advance. Okay? So this is why the problem is tricky. Okay, what do you have to do if you understood all what I was telling you? I told you many things. You have to come to me, and you have to ask me 2 devices and run a Bell test. Okay, why? How come quantum physics violates a Bell test? Bell test, the Bell inequality, is simple mathematics, products and plus and minus ones. So the mathematical reasoning is not wrong, okay? So if you violate the inequality, it's simply because your starting point was wrong. So the objects had not well-defined values to start with. So they did not exist until the moment you make an experiment. They are generated by the experiment, they are random. Okay? Because if someone could predict these outputs in advance, this person can write them, even in a piece of paper. He can write these plus and minus ones for A1, B1, A1, B2, A2, B1, A2, B2. So this quantity is bounded by 2 automatically because of mathematics. Okay? So the only reason why you violate this is because these objects have not well-defined values. Hence they are random. I cannot copy in a memory before selling you the device the outputs. They are random to you, and they are random to me, and they are random to everyone on Earth. Because if there is a person on Earth who can write these numbers, this quantity has to be bounded by 2. So you come and you ask to the provider 2 devices, and you violate the Bell inequality. And then the Bell inequality certifies the randomness of your outputs. And then you can use this for your virtual casino. So this is why in quantum physics you can be sure about randomness, which is impossible in classical physics. And you can do it from the statistics, because in quantum physics you can generate statistics that does not have a classical analog. This is not, I would say, super easy to digest. Okay, well, you know that Einstein didn't like quantum theory because it's random, well, quantum theory is random. And we gave techniques to bound the randomness as a function of Bell inequality violation. Okay, so if you see this Bell inequality violation, you have this amount of randomness. This is the predictability. When you remember the classical value was 2, the predictability is 100%, no randomness. But as soon as you start violating the inequality, you start having some lack of predictability, some randomness. And at the point of maximal quantum violation, that was this 2 square root of 2, you have perfect randomness. So this is a device-independent random number generator. You certify the randomness from the outputs, that is, from the pending quantization. The daemon, then, from the outputs, you can say random. And with this idea, okay, this specified quantum randomness, you can also make cryptography. Okay, so what you need to do is a test between Alice and Bob. A distance, a delta test distance. We know that I get randomness here. I know that Manuel gets randomness there. But remember, the measurements are on a maximally entangled state. I know when I get a plus, he gets a plus. When I get a plus, he gets a minus, he gets a minus. Or when I get a zero, he gets a zero. Okay. So we get local randomness correlated, and this is a secret key. So it's the same idea. Okay, so this is why you can do things in the device-dependent approach, okay? Because in quantum physics, you have statistics that does not have a classical analog. So if you use these statistics, you can make protocols even in the black box scenario. So this is what we do, okay? I don't have time, but this language we use for some other things. We use for foundations and many-body physics and for some other things. So maybe, I know that I'm sort of running out of time. I will tell you another thing, okay? We use this black box language for in many other scenarios and these certification ideas. I will tell you about results on quantum foundations that I like, that we got recently, okay? I hope you are not too tired and you are with me. Okay, so in what I was telling you, we wanted to make protocols in the device-independent scenario, and we used Bell's theorem. So we were using input from quantum foundations to do say things about quantum information theory. Now I'm going to do the opposite. I'm going to tell you something about quantum foundations using quantum information theory. And it's based on this paper that appeared already some years ago in Nature. So basically, somehow we wonder about the role of complex numbers in quantum physics. Okay, so you open a textbook in quantum physics. We were discussing about how to teach quantum physics. I personally like you give the postulates from scratch, okay? It's going to be a trauma to see quantum physics. Why not do it from the very beginning with the postulates? And then you see all these weird Hilbert spaces, and the states are described by vectors, and measurements are described by a basis, and probabilities are computed with the Born rule, and you compose things with a tensor product. These are the postulates of the theory, okay? Perhaps something that is weird is that these Hilbert spaces are complex. Okay. I don't know if it was weird for you. For me, it was weird when I saw quantum physics my first time. Okay, because before quantum physics, it was weird to me, and I was happy to see that it was weird for the founders of the theory. Okay, so even there's a letter from Schrödinger to Lorentz in which he says it's unpleasant to use complex numbers, and probably psi, the wave function, is real. Why it's here, okay? Because before quantum physics, theory
Make
was...
lunch. Why did they all do?
Okay, because before quantum physics, all theories were described with real quantities. I mean, you take Newtonian physics, things are made of masses, forces, speed, velocities, real numbers, okay? You take electromagnetism, you have electric field, magnetic field. It is true that we sometimes use complex numbers to simplify calculations, but it's just a mathematical convenience that we do it, okay? But in quantum physics, the first postulate is already phrased in terms of complex numbers. Okay? And your object, the crucial object, is the wave function side that is complex. So this is why some people care, what happens if we replace complex numbers by real numbers in quantum theory? So, what happens if I do this and I keep all the postulates? Is it a different theory, the same theory? Okay. Okay, here there is something very important you have to understand. Of course, if I change a complex Hilbert space of dimension 2 by a real Hilbert space of dimension 2, I'm going to lose something. Well, for a complex number, I need two real numbers. Okay, I'm going to lose something. But again, dimension is not something that you measure. Okay, it's just a mathematical trick that we use to describe systems. So I want to see if the two theories have different predictions. If they lead to different predictions, then I need complex numbers. If they have the same predictions, the use of complex numbers is simply a matter of mathematical convenience. Okay, I'm going to be fast here. I'm only going to tell you why the problem is not so easy. So let me take okay, you can see this as a game. Okay, so there is Manuel. He's a complex quantum physicist. I'm saying complex, meaning that he's a complex person, but he's a person who believes in quantum physics with complex numbers. And I'm a real quantum physicist. Again, it doesn't mean that I'm a real better than Manuel, but it means that I am a believer of quantum physics with real numbers. This is similar to what happens with Bell theorem. There is some person who believes in local field variable models and a quantum physicist, and there is a game between them, okay? So now Manuel has to find an experiment that I cannot reproduce with my theory. He has to falsify my theory, okay? To persuade me that I need complex numbers in quantum theory. Is that clear to everyone what I'm trying to do? Okay, Manuel is perhaps a complex quantum physicist, but he's not a complex person. He will try the simplest thing, which is, okay, you make some measurements on a quantum system. Probability that described by this trace of rho and the measurements, okay? A projector. He comes to me and says, okay, Antonio Acín, give me an explanation for this experiment with your real weird quantum theory. And I can always do that, okay? These are complex operators in his language. So what I do, I double the Hilbert space dimension. I can do it. I mean, for me, it's enough to reproduce the experiment with objects in my theory. And what I do, I will add this in these two eigenstates of sigma y, 0 plus minus I1. Okay, it seems they are complex, and I'm not allowed to use complex numbers, but you will see that things won't be complex. Okay. So what I do, I take the complex operator that Manuel is using, and I take the measurement that Manuel is using, and I take this new state and this new measurement. You can see that the resulting object is real. You take the complex conjugate of that, rho goes into rho complex conjugate, and I goes into -1. They are symmetric, so this is real. It looks made of complex things, but if you write a matrix, this is a real matrix. And the same for the measurement, okay? So it looks complex, but it's not, because if I take the complex conjugate, I take the same object. If you compute the probabilities, they are equal here and there. So no matter what he thinks about, I can always find an explanation with my theory. He cannot falsify my theory. So let's think about a Bell test. Well, I'm not going to give you the explanation because I'm running out of time. I can also always reproduce whatever he thinks of making a measurements on an entangled state with my theory. So people thought that it's not a difference in predictions between complex and real quantum theory. Okay, we proved this not to be true. Okay, so we gave a slightly different experiment made of complex objects, and we proved that if you replace these by real objects in any possible dimension, you cannot reproduce this complex quantum physics experiment. So we gave the first experiment in which you could falsify real quantum theory, and then, as for Bell theorem, the only thing you had to do was to go to the experiment, to the lab, make the experiment, and falsify this, and prove that you need, if you believe in the postulates of quantum physics a la Hilbert space, you need quantum complex numbers. If you put real numbers, you have a different theory. So the logic is again the same. From theories, I can describe my structure of correlations. I can compare theories because they give different correlations. Then I go to the lab, I measure the statistics, and I can falsify physical theories. So we did that in this paper, and then the experiment came. I mean, we knew when we published the paper, it was a theoretical proposal. The theoretical proposal was within reach. And soon after the experiment, the theoretical proposal was published, there were two experiments which participated in these two. In this second one, in China, falsifying real quantum theory, and then proving that you need complex numbers in quantum theory. Okay, now, I was not going to explain this, okay, but I can tell you many more things if you are interested. So I know I go to the end. So, this is what I wanted to tell you. We came to this device-learning approach based on this fact that there were hacking attacks and we want to make quantum information theory with black boxes. And that, it's very nice for me because I really like Bell's theorem, and what we have to use is the Bell inequality violation to make protocols in this theory, because you want to have statistics that it's impossible in classical information theory, that is statistics that violates Bell's theorem. Then I briefly told you about protocols for random generation, cryptography. So we are working on understanding what you can say and what you cannot say in this scenario. Of course, you have to understand that working with black boxes is nice, but it's also a bit limited. Okay, because sometimes if you add more structure to the boxes, you can say more things about these boxes. Okay, this I think I have time, and we are using the same techniques that we developed this in other situations. For example, in many body physics now, we are also working we're also moving in the direction of many body physics. And I briefly told you about the result in which we could classify quantum physics based on real numbers. Okay, and more in general, we are always interested in this problem of certifying that things behave as expected. Okay, that's all. Thank you very much for your attention.
Here we have time for questions.
Yes, thank you for the very nice and very clear explanations. So it's about the last part about quantum mechanics number. But of course, we know that there is the Hardy formulation of quantum mechanics in terms of probabilities, which are your objects for the Bohm theory. So those theories don't use quantum mechanics number. So can you elaborate so what is precisely the need of you cannot use quantum?
Yes, yes.
Maybe Tony, can you briefly summarize the question because I have no microphone?
The question is that, let's say, we are considering the standard formulation of quantum theory based on Hilbert spaces, which I would say is the one that most people use, but there are other formulations of quantum theory a bit less standard, like there is Bohm theory, and there is also a new derivation of, I'm not sure if Hardy derives the whole quantum theory, but okay. There are some other derivations in which people don't use complex numbers. Okay, yes, I agree. So maybe I went too fast because I wanted to explain it because I like the result. So what we falsify is the Hilbert space formulation of quantum theory, because Bohm theory is still valid. It's based on real. Everything is real in Bohm theory, and we cannot falsify that. I mean, if you think about it, the falsification of any real number explanation, okay? All what you see when you make an experiment are probabilities. And probabilities are always made of real numbers. Then, to these probabilities, you attribute a meaning through theories. And it happens that in the Hilbert space formulation, we use complex objects to attribute meaning to this probability, and this is what we are falsifying.
Questions?
You always measure the probability with some uncertainty. So, to which extent that you are sure that
Yes.
your method is...
Yeah, so the question is about statistical uncertainty, no? Because, of course, in my talk, I was simplifying things, and I was saying that Alice and Bob have these boxes, they press buttons, and they see outputs, and they accumulate statistics, and they count frequencies, and out of the frequencies tend to the probabilities, no? When you end up to infinity, the number of rounds. So it's true that usually you want to make rigorous, in science, you can never be sure about anything. You always have sigmas or statistical deviation, no? So the logic will be the same, okay? So I will make the Bell test, I will run it a significant amount of times, then I will have some confidence about the value of my Bell parameter with some deviations, and then I will tell you that with these probabilities, these outputs contain this amount of randomness. Of course, things can always, I mean, also if you think about randomness, you can never be 100% sure about randomness because you can do a random experiment. You can have say, a coin, perfect coin. You can flip it n times, and I can try to guess your numbers, and I can be right with probability 1 over 2 to the n. And then these numbers, you use them, and I get your money because I was lucky. So, yeah, there is always this statistical things from the fact that you always run an experiment a finite number of times. But we can accommodate this, okay? So then the statement we say is like with probability larger than that, I can certify that the object is random. Yes.
Questions?
And do you have an opinion about this paper that appears some years ago in Nature that quantum mechanics cannot consistently describe a loop of itself? It's like a well-explained complex version. Do you know that?
Yeah, I cannot.
I don't know.
Okay, so I'm interested in quantum foundations, but I sometimes don't like quantum foundations because sometimes for me it's hard to understand the statements that people are doing in quantum foundations. They become a bit elaborate, no? And I like Bell's theorem because I understand it. It's just this very simple scenario in which outputs are predetermined and you define in this finite friend. Okay, it's a very subjective opinion. I find that even the formulation of the problem I see it less clear. So I cannot, sorry, I'm not going to comment because I don't have any strong opinion.
Questions? Maybe can you comment a little bit where we are technologically? So for the implementation of device-independent cryptography, how far is the technology today?
Well, I have something there. Okay. Okay. So I was telling you that we can buy cryptography today, standard cryptography. So in this sense, the technology is mature. I don't know if you may be aware that there are some efforts in Europe to establish a quantum cryptography network over Europe. Okay, so this is something that can happen. It's not cheap, but it can happen. But then I was telling you that this standard cryptography, you may have hacking attacks a la Makarov. So why not using device-independent cryptography if you solve all these issues, no? Well, this is because it's challenging. So basically, you need to observe a Bell inequality violation at distance. And this, I don't have time to tell you, is very difficult. It has not happened. Having said that, there were, 2 years ago, no, 2022, two proof of principle demonstrations of device-independent quantum distribution, okay? So these people made experiments in which they observed the Bell inequality violation at distance, and they could argue that this could be used to make a secret key and then cryptography at distance. So why there were proof of principle? Because in the first experiments, the distance between Alice and Bob was 2 meters, okay? Of course, you don't use cryptography for people who are distant 2 meters, okay? Because they make 2 steps and they communicate the secret. It was just showing that in principle, if they could scale the distance, they could do it. But okay, scaling is not as simple as it may seem, okay? The second one had a larger distance, 400 meters. I don't have, it's related to the problem it was mentioned before. The experiment was so slow that the statistical fluctuations were too large to conclude with enough probability that they had a key. So what they were telling you is like, we have these conditions. If we are able to run the experiment longer, but this may take years with the given rate, we could conclude that we have a quantum distribution, but okay, they couldn't. So this is why they were proof of principle. It's challenging.
Follow up on that. So these are using trapped ions and trapped atoms.
Yes.
For a reason they can't use photons.
Yes.
More standard.
Yes. So what is the main enemy for running this? So we have to see a Bell inequality violation at distance. So the main enemy to see a Bell inequality violation is losses. So if I send a photon to Manuel and I'm in Barcelona in Valencia, the most likely output is going to be no click, because the photon will get lost. So it happens that the table of probabilities that I wrote you with plus and minus 1, you will add a new element, which is plus 1, minus 1, or no click. And when the losses are large, but large means larger than 50% or 60%, none of these probabilities violate a Bell inequality. So this is why it's so challenging to violate a Bell inequality distance, because usually you're connected by a fiber optic. Losses in the fiber optic are exponential with distance. No way you can do it. This is why these people had to do it with an atom and the photons. It's more complicated. I don't have time to tell you, but yeah, this is why it's difficult. Direct transmission does not work.
Okay, Amanda.
I have the impression that there is much more effort being developed post-quantum cryptography discussed quantum cryptography.
Yes. Well, the question is about post-quantum versus quantum distribution. So the problem is that our standard cryptography is based on factorization, a mathematical problem. And this problem happens to be easy for quantum computers. So people are trying to think, like, what do we have to do to have secure schemes against quantum computers? So there are two options. The first option is like, okay, I'm going to base my security on, I still base my security on mathematics. I only have to replace factorization by another problem, hoping that this problem is hard for quantum computers, okay? And the second option is like, okay, I'm not going to base my problems on mathematical complexity, I'm going to base on the laws of quantum physics, and you have quantum distribution. Okay, me as a quantum physicist, I prefer to base things on the laws of quantum physics than mathematical complexity. The problem is that in the quantum cryptography, you have to buy new devices, new hardware, expensive. In the second solution, you have to change factorization by a different problem. It's a change of software, much cheaper and easier to do. So this is why people are saying, don't do quantum cryptography, just change your software, and that will be enough. Okay. I think at the very end, when I talk about cryptography, there is nothing like security from scratch. So every protocol is based on some assumptions. So in post-quantum, people will tell you, I assume that this problem is hard for a quantum computer. And me, I will tell you, I assume the devices are governed by quantum physics. And then we make a protocol with some cost and with some performance. And then it will be the customer who decides, okay? The problem I see is that all the people saying that post-quantum is better, usually they are not physicists. So we shall say. I mean, let me tell you that the National Institute of Standard and Technologies, for post-quantum, you have to invent post-quantum protocols. You have to find a problem that is hard for a quantum computer and show how this can be used to secure your messages. So they launched a call to select some of these problems. There was a competition. People were selecting candidates. They made a ranking. They selected, I believe, 4 candidates. This is secure, okay? And they had some backup options. They were also secure, okay? But backup. Then someone with classical laptop hacked one of these backup options. So unfortunately for me, he didn't hack the ones in the top, and it would have been amazing, okay? But he hacked the backup. So factoring, which is the key for security now, is based on the fact that we believe that factorization is hard because human beings, we have been trying to factorize large numbers for centuries. But these problems, how do we know they are complex? How do we know they are complex even to a computer that we don't have today? So there are some risks as well.
Okay, I don't see any more questions, so I suggest we thank Tony.